In this problem, we are given two wheel loads of 40 kN and 60 kN separated by a distance of 5 meters, which will pass through a simple span of 10 meters in length. We are tasked to find the maximum moment developed in the beam. And to solve this problem, first we need to find the resultant of the two loads. Let's say it's found right here. That is equal to 60 kN plus 40 kN equal to 100 kN. And the maximum moment typically occurs if we place the median of the resultant and the largest load, that is 60 kN, is placed at the midspan or the center line of the beam. Now, we need to solve for the distance of the 100 kN force, that is the resultant, from the 40 kN force. So let's take this 40 kN as our reference axis. We call this x. To solve for the distance, we take the summation of moment at the x-axis, which is this one, equal to the resultant force times its distance or moment arm distance from the axis. We have 40 kN times its moment arm distance of 0 since it's at the axis, plus the 60 kN force multiplied by its moment arm distance of 5 meters, equal to the resultant, that is 100 kN times its moment arm distance, which we need to solve. So 40 times 0, that's 0. 60 times 5, that's 300 kN meter, equal to 100 kN times x. Dividing both sides by 100 kN, we get 3 meters equal to the moment arm distance. And that is our distance from the axis to the resultant force, equal to 3 meters. Now that we have our distance, let's solve for the other dimensions. Since we placed the 100 kN force and 60 kN force at the center line, we have 5 minus 3, that's 2 meters, between the 160 loads, divided by 2, that's equal to 1 meter. And for the other distance, since it is half the midspan, which is 5 meters, minus 1, so this remaining distance here is equal to 4 meters. And this is half a span of 5 meters minus the distance of 1 meter and 3 meters. This remaining distance here is equal to 1 meter. Now to solve for the moment, we first need to solve for the reaction at the supports. So let's take this point as point A, and this reaction here called RB. We can take summation moment at point A equal to 0, considering counterclockwise to be positive. So we have the 40 kN force inducing a clockwise moment, so it's negative, times its moment arm distance of 1 meter, minus the 60 kN force times its moment arm distance of 6 meters, plus the reaction at the support RB multiplied by its moment arm distance of 10 meters. It's positive since it's acting in the counterclockwise sense, all equal to 0. We have RB that is equal to RB equal to 40 kilonewtons. Now we don't need to solve for the reaction at A, because what we'll do is to cut the beam at the largest load, that is 60 kilonewton, and expose the moment, bending moment, and shear at this point here, which is where the maximum moment is located. So let's say we have a moment here called Mmax that we need to solve, and a shear force called V. We have reaction here of, this is 40 kilonewtons, which we solved earlier, and a distance of 4 meters. Now we can solve for the moment by taking summation moment. Let's call this point O. So by taking summation moment at point O, we have the clockwise moment called Mmax. This is negative since it's clockwise, plus the 40 kilonewton force inducing a counterclockwise moment with a moment arm distance of 4 meters equal to 0. And we can solve for Mmax, that is negative x plus 40 kilonewton times 4 meters equal to 0. Shift solve, we get Mmax equal to 160 kilonewton meters, and that is our final answer.